Imagine you are handed the simplest equation you have ever seen. A child could write it down. A child could understand what it is asking. But no human being in history, not Euler, not Gauss, not Ramanujan, has ever been able to prove it. You sit down and try. You spend a week on it, a month, a year. You realize this problem has already consumed the lives of the greatest mathematical minds who ever lived, and it still has no solution. This is perhaps the hardest and most dangerous problem in all of mathematics. And there are really three possible outcomes. Either someone eventually cracks it and rewrites the foundations of math as we know it, or it remains unsolved forever, passed down from generation to generation like an inheritance no one can spend. Or, and this is the most disturbing possibility, it turns out to be one of those rare statements that is actually true, but can never, ever be proven. This problem has consumed mathematicians for over 160 years. Today, we are going to try and understand it together. Let me ask you something you probably think you already know the answer to. What is a prime number? The obvious answer, a number divisible only by 1 in itself. 2, 3, 5, 7, 11, 13. You learned this in school. It feels settled. Simple, almost boring. But go deeper. How are primes actually distributed across the number line? Is there a pattern? Could you sit down right now and write a formula that tells you where the next prime falls? You cannot. Nobody can. And the further you go along the number line, the stranger things get. Because here is the thing. Primes are not random. They are completely determined. There is no dice being rolled. Every prime is exactly where mathematics puts it. And yet, no human being has ever found the rule that places them there. This matters far beyond pure curiosity. Primes are the skeleton of modern mathematics. They are the basis of every encryption system protecting your bank account, your messages, your data. The entire architecture of digital security is built on the assumption that prime numbers behave in certain ways, and we have never actually proven that they do. Maybe this means there is some hidden structure underneath some deeper truth about numbers we have not yet found. Or maybe there is not. And that is the most unsettling possibility of all. This is the Riemann hypothesis. And to understand why it has never been solved, we need to go back to the beginning. The best way to approach this problem is to first understand what mathematicians actually mean when they talk about the distribution of primes. Around 300 BC, Euclid proved something remarkable: primes never run out. No matter how far along the number line you travel, you will always eventually hit another one. The proof is clean, elegant, and about half a page long. That part we have known for over 2,000 years. The harder question is how they are spaced. In the 1790s, a 15-year-old named Carl Friedrich Gauss began counting primes by hand-tallying how many existed below 100, below 1,000, below 10,000. And he noticed something. The further out you go, the more accurately you can predict roughly how many primes exist below any given number. Not exactly, but approximately. The density of primes near a large number n is close to 1 divided by the natural logarithm of n. This became known as the prime number theorem. It is a beautiful approximation, but it is just an approximation. And the gap between the approximation and reality, that error term, is where the real mystery lives. In 1859, a German mathematician named Bernhard Riemann wrote a single 8-page paper. In it, he took the question of prime distribution and translated it into a completely different language, the language of complex numbers. He defined a function, now called the Riemann Zeta Function, which takes a complex number as input and produces a complex number as output. What Riemann showed was extraordinary. The places where this function outputs 0, the so-called zeros of the zeta function, are directly connected to the error in the prime number theorem. The zeros tell you exactly how wrong your approximation is. They encode the rhythm of the primes. So what if we could locate every single zero? The zeta function has infinitely many zeros. Some are obvious, called the trivial zeros, sitting at the negative even integers. But there are infinitely many others, spread through a vertical strip of the complex plane called the critical strip. These are the non-trivial zeros. And here's the observation that started everything. Every single non-trivial zero that Riemann and every mathematician after him has ever examined sits on one specific vertical line running through the critical strip, the line where the real part of the input equals 1/2. This line is called the critical line. Riemann's hypothesis is simply this: all non-trivial zeros lie exactly on the critical line. That is the entire conjecture. One sentence, and no one can prove it. Here is how far we have actually gotten. Mathematicians and computers have now calculated and verified over 10 trillion non-trivial zeros of the Riemann Zeta function. 10 trillion individual points, each one checked, each one sitting exactly on the critical line, right where Riemann predicted. Not one exception, not one outlier. 10 trillion confirmations in a row. And it means almost nothing. This is the part that separates mathematics from every other field of human knowledge. In physics, 10 trillion confirming experiments would be considered proof beyond any reasonable doubt. In mathematics, it is considered a good sign and nothing more. Because mathematics does not work on evidence. It works on proof. And a proof must hold for every case, not 10 trillion cases, but all cases, across the entirety of infinite numbers. A single counterexample, hiding somewhere out in the infinite expanse of the number line, would collapse the entire hypothesis instantly. Despite every zero ever computed confirming the hypothesis, we are no closer to a proof than Riemann was in 1859. And this is not a hypothetical concern. Mathematics has been burned before. There is a result in number theory concerning the prime counting function, comparing it against a specific approximation called the logarithmic integral. For every number anyone had ever checked, the prime counting function was smaller. For billions upon billions of cases, the pattern held perfectly. Then, in 1914, the mathematician John Edensor Littlewood proved that the pattern must eventually reverse infinitely many times. The first number, where it actually reverses, is estimated to be around 10 to the power of 316. That is a number so large it has more digits than there are atoms in the observable universe. You would never find it by counting, but it is there. Patterns in mathematics can hold for incomprehensibly large stretches before finally breaking. The verified zeros of the Riemann Zeta function could be the beginning of a pattern that holds forever, or they could be the beginning of a pattern that breaks at a number so large no computer will ever reach it. We do not know, and right now we have no way of finding out. So why is the sky, or rather the number line, not uniformly lit with primes? The zeros of the zeta function encode the error term in the prime number theorem. They describe, with exact precision, how the actual distribution of primes deviates from the smooth approximation Gauss found. If all the zeros really do sit on the critical line, exactly where Riemann said then, those deviations are as small and as regular as they could possibly be. The primes are distributed about as evenly as their nature allows. The apparent randomness you see when you look at the number line has a hidden order underneath it, a rhythm, a structure. The primes are not random. They are just playing by rules we have not yet managed to write down. To go beyond what computation can verify and figure out whether the Riemann hypothesis is actually true, we first need to understand what kind of problem this really is. The intuitive assumption is that a pattern this consistent 10 trillion zeros, not one exception, must be provable. Surely the universe of mathematics is not so cruel as to make something this regular fundamentally beyond reach. This is what most people feel when they first encounter the problem. But in 1931, a mathematician named Kurt Gödel published a result that permanently changed what we believe mathematics is capable of. His incompleteness theorems proved that in any sufficiently complex formal mathematical system, there exist statements that are true but cannot be proven within that system. True, unprovable, the two are not the same thing. This was one of the most disturbing discoveries in the history of human thought, the idea that mathematical truth is larger than mathematical proof, which means there are really three possible structures this problem could have. First, the Riemann hypothesis is true and provable, but the proof requires mathematics that does not yet exist. It is waiting to be found by someone who has not been born yet, using tools that have not been invented yet. Second, the Riemann hypothesis is true, but unprovable within our current formal systems. It is correct. The zeros really do all sit on the critical line, but no sequence of logical steps within standard mathematics will ever demonstrate this. It is a Gödelian statement about numbers true and forever out of reach. Third, the Riemann hypothesis is false. There exists a non-trivial zero sitting somewhere off the critical line, but it is so deep in the complex plane, at such an astronomically large scale, that no computation in human history has come close to finding it. Mathematicians have spent decades trying to determine which of these is most likely. The strongest circumstantial case comes from connections that nobody expected. In the 1970s, mathematician Hugh Montgomery was studying the spacing between Riemann zeros when physicist Freeman Dyson pointed out something remarkable. The statistical pattern of those spacings matched almost exactly the energy level spacings found in certain quantum systems. Random matrix theory. Quantum chaos. The zeros of a number theory function and the energy levels of physical systems were following the same distribution. This was not supposed to happen. There is no obvious reason why the structure of prime numbers should have anything to do with quantum mechanics. And yet, the connection is real, reproducible, and still not fully understood. Most experts believe the hypothesis is true. The evidence, numerical, structural, physical, all points in one direction. But belief is not proof. And here is the part that should make you uncomfortable. What if our entire mathematical framework is simply too small to contain the answer? The history of mathematics is a history of discovering that the universe of numbers is stranger and larger than any previous generation imagined. Every time we have been certain we understood the shape of things, mathematics has shown us a room we did not know existed. This is what most mathematicians believe today, and it has some genuinely unsettling implications. If the Riemann hypothesis is true, then the primes are distributed with the maximum possible regularity. The error in our approximations is bounded, tight, controlled. This has direct consequences for cryptography. The mathematical guarantees underlying encryption become stronger, more predictable, better understood. But if it is false, if even one zero sits off the critical line, then the distribution of primes is more erratic than we thought. Not chaotically erratic, not unpredictably random, but irregular in a way that could, in principle, be exploited. The encryption systems built on assumptions about prime behavior would not necessarily collapse overnight, but they would be resting on a foundation with a crack in it. Now take this further. Right now, somewhere in the world, a mathematician is sitting in a quiet office, staring at a notebook. They have been working on a particular approach to the Riemann hypothesis for 3 years. They do not know yet whether the argument holds. They are checking it line by line. If they are wrong, the notebook goes in a drawer and the world never hears about it. But if they are right, if the argument holds, and the hypothesis falls the moment that paper is published, the entire field of number theory reorganizes itself overnight. And the security assumptions baked into the internet begin to be questioned at a level they have never been questioned before. This is not a thriller plot. This is just what mathematics does. Quietly, patiently, indifferent to whether we are ready. There is a $1 million prize attached to the Riemann Hypothesis 1 of 7 Millennium Prize problems designated by the Clay Mathematics Institute as the most important unsolved problems in mathematics. Of those 7, exactly 1 has ever been solved. The Poincare conjecture, resolved in 2003 by the Russian mathematician Grigory Perelman, who then declined the prize money and largely withdrew from mathematics entirely. 6 remain. The Riemann hypothesis is the one that mathematicians most consistently describe as the hardest, and here is why it does not feel arbitrary. Numbers are not invented, they are discovered. The integers exist independently of human thought 2 plus 2 equaled 4 before there were humans to notice it, which means the primes exist independently of us as well. They were always there, arranged in whatever pattern they follow, governed by whatever rule we have not yet found. We are not trying to build a solution. We are trying to find one that already exists, somewhere in the structure of mathematics itself. The pattern is real. We just cannot see all of it. Do you remember the critical line we talked about earlier? Every verified zero sits on it, 10 trillion of them. And yet the critical line itself, the full infinite extent of it, remains uncharted. We have explored a finite stretch of an infinite object. The rest of it extends outward forever, and we have no way to follow. This is not a limitation of our computers. Faster processors will not solve this. It is a limitation built into the nature of infinite mathematical objects. You cannot verify an infinite set by checking its members one at a time. Not in a year, not in a billion years, not ever. The lock is not technological. It is logical. Every year, some of the most talented mathematicians alive dedicate significant portions of their careers to this problem. Partial results accumulate. Connections to other fields deepen. The surrounding landscape of mathematics becomes richer and better understood, and the hypothesis itself remains exactly where it was in 1859 unproven. Think about what that means over time. In 100 years, if it remains unsolved, it will have outlasted every mathematical tradition of the 20th century. In 1,000 years, if mathematics as a discipline still exists in a recognizable form, someone will still be able to walk up to a board and write down the same one-sentence conjecture Riemann wrote in 1859. Nothing will have changed. The problem does not erode. It does not become easier with time. It simply waits. If a mathematician born 500 years from now encounters this problem, they will have tools and frameworks we cannot begin to imagine. The mathematics of the 26th century may make our current approach look like trying to measure the ocean with a teaspoon, and perhaps they will find a proof clean, complete, inevitable, or perhaps they will find something Gödel would have recognized immediately. While an unsolved problem might sound like failure, it is not. The mathematics built in the process of attacking the Riemann hypothesis has already permanently changed number theory, analytic mathematics, cryptography, and theoretical physics. The connections uncovered between prime distribution and quantum mechanics alone represent one of the stranger and more beautiful surprises of the last century. None of that would exist if the problem had been solved quickly and cleanly in 1860. The hardest problems in mathematics do not just produce solutions, they produce entire fields. If you have made it this far, you now understand the Riemann hypothesis better than most people who have never studied mathematics at university level, what it claims, why it matters, why it resists proof, and what it would mean if it fell. That is not a small thing. Go tell someone about the critical line. Tell them that the primes have a hidden rhythm we can hear but cannot explain. Tell them that 10 trillion pieces of evidence add up to exactly 0 proof. Mathematicians will keep working on this. The problem will keep waiting. And somewhere in the future, someone will either find the proof or find the proof that there is no proof. Either way, the universe of mathematics will turn out to be stranger than we currently believe it is. It always does.